And I gave him 4 marks, I think. Entertainment value, I mean, you got to appreciate, no? Since my last morning, I would like to say that I have enjoyed this session. It's been a very intense session, but I would like to say I have enjoyed it tremendously, and I hope you have enjoyed it as much as I have. So as a wrap up for this morning's session, I hope to touch on a couple of examples. They are not recent examples, but they are examples that, in a sense, to me, best illustrate what FEM can do for you if you do a proper job. So they are not the most recent examples in my consulting, but some of the recent examples are fairly routine thing. I thought they are fairly routine. There's some nice thing, but they're fairly routine, and there's nothing to show people that the thing actually worked. Whereas these 2 examples, there's some form of validation, some comparison with field data, field observations, that kind of thing. So you are able to see, okay, does the FEM actually work, or is it giving rubbish? So basically, I thought that this will be useful. And the first example, 2 examples, the first 2 different examples, and they deal with different things. The first example is an example of a collapsed structure, factor of safety probably less than 1, when you look at it properly. And it is a strength governed problem. The second example is an example that is of a very, very safe structure. It's a stiffness governed problem. So we can compare and contrast the 2 examples. Okay. So basically, back analysis of the Nickel Highway collapse on the 20th of April 2004. Okay. Now, when I first started this, when I give you the notes, I thought I would just give you an abridged version because I do not know how much time I have. But before I start, is there some interest to know a bit more detail about this? Because I have another set of slides that are quite detailed with animations and things, which actually I showed years ago in Bombay, IIT Bombay. But maybe by that time you were not in university, not here yet, or not in university, whatever. No, it's Bombay, I think Bombay. What we have learned. No, I thought it's IIT. Yes. Not last year. Last year I was talking about let me just take a look. I probably have the date here somewhere. Yeah, but let me just take a quick look, because I have all the shortcuts here, so it's not a problem. Not a problem. Let me just take a look at the shortcut. Quite a few years back, yeah. Did any of you attended the ATC workshop? 18 workshop? No, okay. So you want to maybe just quickly run through some of the things, maybe just to get, because it is such a big event and it haunted the psyche of Singapore geotechnical engineers for many, many years. Even now, we are still, in a sense, guided by a particular incident. Just to give you a quick background, okay? Basically, the Nickel Highway station is part of this circle line. Alright, and it's actually down here. This is a circle line. Actually, the circle line, I can tell you by just an aside, the circle line is a stupid example of stupid planning. They did the circle line, but they refused to close the gap. So the train has to go, it's not a circle. They go up this way and then come back this way. I said that is stupid. So now they realize that there is a real problem. And now they start to close the gap. You tell me the Singapore government has never made stupid mistake, that's rubbish. Okay? It's just that they refuse to admit it. Okay? So anyway, the Nickel Highway is the one with the pink dot, the pink dot over there. See? There's the Nickel Highway station. Okay? It's part of the circle line thing. And the circle line is now largely operational. Okay? And this is how the station, you can see there's a break in the circle line. It's not a circle, it's a 3/4 circle. Okay? And this is roughly where the station is. The station is actually here. Somewhere just down below here. Okay? So this is where the station is, and it's that particular stretch is around the southern part of Singapore, where there's a lot of deep marine clay. Okay? And this is a aerial view of the site. And this is the stretch that collapsed. This is the launching shaft that you saw yesterday. This is what you call the M3 section, M2, M3. This is the section that collapsed. Okay, the whole thing here. Okay, and opposite here, that the nickel highway is the road that kind of run parallel. This is the nickel highway. Okay, and because that thing collapsed, the nickel highway was closed to traffic for several months. Okay, there was a major collapse. And this is the Golden Mile complex. And during the collapse, there was a lot of concern that the Golden Mile complex may be compromised by the collapse. Okay, this is a close-up view of the collapse. Now, you can see actually there is some complication in the site even as it is. And there are some funny thing that the contractor actually did, which I totally disagree with. And I think we shouldn't do this kind of thing. Basically, firstly, there is actually a very large power cable, 66 kilovolt cable crossing here. Now, no one is supposed to do anything to that cable. If you cut that cable, I think half of Singapore will have no electricity. Okay, so that is the kind of importance. So that during that particular excavation, it was decided that that cable cannot be cut. It has to be there. And because the cable was there, all right, and it's a fairly big cable, you cannot cast the diaphragm wall. The diaphragm wall cannot be cast because you need a machine that go through and kind of dig the soil out. If you cannot move the cable, you can't do anything. There's nothing you can do. So there was actually a gap there, which I think, on hindsight, to me, that is actually not a good move to solve. Just leave the gap there. I think people should do something like a grouted soil block to at least make sure the gap is filled up. So there was a gap there. They try to fill up the gap as they go down by patching it up with like shotcrete and some steel reinforcing. But I think it's a really bad, poor attempt. The second thing that I like to draw your attention to is these things. You see, these are the bracings, the struts, right? But there's no continuous veiler going across. And the struts are all sort of like, these are very short veilers, short lengths that kind of join the struts to the wall. And the panels are not one-to-one joining. They are not one. It's a very, very haphazard kind of a construction. And in fact, people have highlighted it to the Japanese contractor. The Japanese contractor's response was very straightforward. We used it in another site called Boulevard Station, and it worked. So it should work now. So that this is the kind of mentality in those days. Really cowboy mentality. The soil profile, very deep marine clay. These two layers are deep marine clay. There's a thin layer of fluvial soil around here, okay? But this is very deep marine clay, 30 over meters, okay? It's not the deepest in Singapore, but it is almost the whole depth of the entire excavation, all right? And this is the view of the excavation. Now, the excavation was required because there was an interchange, the four tunnels interchanging each other, and so they have to cast that station box into the interchange. So not the station box, they have to cast the interchange into a box configuration. And in order to cast that box configuration, they have to dig down 35 meters to cast the box and then fill 30 meters. That is the kind of scenario. But 30 to 28 meters, that's the kind of that's kind of scenario that was taking place. And so there was something like 9 to 10 layers of strut being planned. 2, 4, 6, 8, 2, 4, 6, 8, 9, 10. There's another layer of struts there. So 10 layers of struts. These 2 layers of soil are jet grouted layer. Jet grouted layer in the sense that they want to improve the layer of soil to give it additional bracing. Okay? And then the idea was that when they come down to this layer, they're supposed to cut away this layer, excavate that layer of jet grouted soil and remove it. Okay? And actually, it was when they are removing the jet grouted soil that the whole thing collapsed. Whole thing actually collapsed. So this is the situation. And so basically, the contractor is Nishimatsu Lam Cheng and Monso Consultant. You see, that was an old name for AECOM. AECOM absorbed Monso Consultants after that, after 2005. And so there was a whole string of subcontractors, I won't mention all of them. So this is the project team. Of course, the main contractor is Nishimatsu and Lam Cheng. Lam Cheng is just a local name, a local guy who land the name in and collect some money, but he actually doesn't do much of the work. Most of the work is done by the Japanese Nishimatsu. Okay, so these are some of the... You see, even before the collapse, there have been a whole string of incidents: excessive deflection, excessive deflection, excessive deflection, excessive... I mean, when you see a whole string of incidents like that as an engineer, something must be like, alarm bell must be going off, in the mind, But somehow people are still pushing on as though nothing has happened. So, they were sort of like pushing ahead, just making sure that they meet the timing. But actually, the design was all wrong. In fact, one of my friends was looking at it from a building that, it's a core concourse building. It's about 600 meters away from the site, overlooking it. He was looking down. He's an Indian, one of my Indian friends. He's a boss of a big of Golders, one of the managing directors in Golders in Singapore. But before that, he runs his own company. He was telling me, he said, I looked down from the window. The first thing I asked Peter Lee was the Chief Executive Officer of Monsell Consultant, and so he was implicated. The first question I asked Peter Lee was, how can such a flimsy structure support such a deep excavation? All in soft clay, 20 kilopascal. The wall is only 800 millimeter thick. He said that from my experience, you look at it, it won't stand. It won't stand. And the struts are too flimsy. So basically, already a lot of people are saying, this is just, it's not going to work. But then, these are all people who are unrelated to the project. So the contractor doesn't have to listen. It's a design and build project. Design and build means the contractor priced in the design, the building, everything. So the Monsell consultant, which is the consultant, actually comes under the umbrella of the contractor. And when they were tendering, the price that Nishimatsu Lamcheng gave was 70% lower than the next lowest bid. I mean, this is another thing, I mean, if you are the client, and you are evaluating contract, the first thing you see is something like that, and then all the other people are bunched up around here, the pricing is bunched up, and then suddenly there's one guy that's right down at the bottom. What is your thinking? I better call up this guy and find out what the hell is going on with this guy first. That must be the situation. Why is he able to do it so much cheaper? And either he's got some incredibly innovative system that other people cannot think of, or he's taking a lot of unnecessary risk. It must be. You see, this is the kind of thing that as engineers you must bring out there and sort of make sure that, I mean, a lot of it is not exactly technical, but the ability to kind of spot a dangerous situation before it actually becomes a reality, to me, is part and parcel of engineering. And there's no fooling around this kind of thing, because there's a lot of things can happen. Okay, anyway, you can see that there's a chronology of event on the 20th of April 2004, and around 8:30 they already noticed all kind of sound coming out, all kind of sound coming out. The things were buckling, the joints were buckling, the strut whaler connections were all buckling. Okay, the struts were buckling. So basically, frequency about 4 to 5 times a 10 minutes interval. And so I went into the excavation base for inspection. They saw a group of workers preparing to install a 10 level of strut at this. These are the strut sections. Another group of workers was carrying out excavation. They hear another sound. So a lot of this thing going on already. And notice that the top C section has completely buckled slightly inwards, and the inner flange of the whaler had buckled downwards by about 5 centimeters. He heard another flunk of tongue about a few minutes later, and looked for it and found whaler 335 has buckled. This thing is now 30 meters deep below the ground surface, and these people are working there, and you see the struts buckling one by one. What would you do? Honestly, I don't know why they are still working there. I would have come out to the ground surface. I mean, look, the thing is buckling. Obviously, it's going to collapse, right? So basically, to me, this is just total mismanagement. Okay. So basically, after that, at 9:30, that was only in the morning, okay? And then they saw buckling of the strut at 336. You can see 335, 336. They go progressive, section by section, okay? And then somebody saw another 2 meter strut at somewhere near 336, 337 that were a bit buckled. And so then 337, 338 has sagged. Again, you see, the next section is progressive collapse. At about 10 a.m., somebody checked the strain gauge reading and told him that there was abnormality in the reading. All these kind of things are going on throughout the day. And there are still people going up and down, up and down, up and down. I mean, I just find it amazing. Okay. And so site inspection at 10:30, and he noticed that the whaler at 335, 336 north have buckled. The 4 of them discussed the following contingency plan: adding concrete to strengthen the whaler. Hey, come on, it's too late, no? The concrete takes 28 days. How can you pour concrete in and expect it by afternoon to have the strength? It's not going to happen. You know what I mean? It's a very, very lame attempt. Alright? You need Superman to do this. Okay? So anyway, these are some of the photographs of the buckled joints, And then at about 11 a.m., quarry worker removed the welding tools and sets from the excavator. I think preparing to pull out. It's getting a bit too dangerous. So excavation operators level the excavation base so that lean concrete can be poured. What are you talking about pouring lean concrete? I mean, 28 days to gain the strength, and now you the strut are buckling and you're pouring. Lunch break at 12 noon. At about 1 p.m., the daily coordination meeting by this, provided inclinometer reading show a deflection of 441 millimeters. It's that much, you know. I mean, okay, an increase of 90 millimeter from the reading taken 3 days ago. So you can imagine the increase in the reading. The design value of 395, which was twice revised previously, this is the already revised upward twice. Originally 150, then I think 200 something, and then now 359, and then now it's shot to 441. You know, so has been exceeded. You see, this is the mentality of a contractor. This is contractor. They quite normal. It cannot be happening to me. It's kind of a refusal. It's a denier of the situation. It cannot be happening to me. This cannot be happening to me. It cannot be failing. You know what I mean? The refusal to accept the reality of the situation. So he checked anyway they continued to check the strain gauge reading and found that it has dropped significantly. Of course, the blooming thing has buckled. How can it be taking any load? You know? So they were pouring concrete inside there, and then the strain gauge actually dropped. Anyway, you can see this thing. Okay, at about 2:30, okay, by 12:30, they already closed the nickel highway to traffic. Thanks goodness, they closed the nickel highway to traffic. Okay, because they noticed that this ain't gonna work. Okay, at 2:30, the workers have poured concrete to the top section. He noticed that the whaler have buckled. You see now the whalers are buckling. Okay, the whalers are the thing that sort of line the wall from the struts, right? The downward sagging of 335 south was about 20 centimeters. You know, worse than that observed by someone else in that morning. So 5 cm increase of sag in one morning. You know, and the tongue sound were getting more frequent. Okay, they were getting more frequent. And he then noticed that the whaler, there was a lot of things happening. Okay, and the collapse finally happened. There was a earth caving in. It wasn't like suddenly, it took over more than half a day. All right, so actually there is ample time for people to get out. But in spite of that, 4 persons died. 4 persons died. And the bodies of 2 of the persons were never recovered. Okay. So the collapse happened at about 3:30, and you can see this was before the collapse. They were doing all kinds of things. This was the collapse taking place. This happened because the collapse broke a gas pipe. And so the fire came out. Okay. So there was fire as well. And then this is the collapse happening halfway. This was around just before I think it will be about early afternoon, 2:30, 2 o'clock, that kind of thing. You know? So basically, this is what happened. So anyway, now I already talked about the method A, method B, so I won't talk about this. I will skip all this thing. Okay? I will skip all this thing. And I want to talk a little bit about the analysis. Now, after the collapse, we were asked by the Land Transport Authority, who is the client? The Land Transport Authority is in charge of all land transportation system in Singapore. Development, including train, subway, train, road. Okay, so everything on the land is coordinated or taken care of by the Land Transport Authority. So we were asked to see if we can use through some kind of analysis, at least try to simulate the collapse process and provide some insight into the collapse process. Okay. Originally, some IT guy was saying, why don't we just simply do it by man? We just think we're going to collapse like that, and then we just simulate that using what SolidWorks or whatever the case may be. And immediately the engineers ruled them out. I said, oh, this is rubbish. You are just imagining what is going to happen. You really need something to calculate the situation and get the thing going. So basically, we were asked to do it. And this was our final element mesh. We did this using Abacus, which we, at that time, and even now, I think is the only tool that is widely available that you can use to model this thing. And so we did a total stress analysis, okay? And the reason is because we really don't know enough. And the second thing is, of course, we need to make sure that we reproduce the shear strength, the undrained shear strength of the soil. And one of the way to do that is to use method C. So we are actually using method C to do that. So don't ever think method C cannot work. It can work in the right circumstances. So basically, up to level 10, up to the 10th layer, we were doing static analysis. And at the 10th layer, we switched to dynamic analysis. Abaqus has this ability to switch between stages. And the reason why we switch into dynamic is because the 10th layer is the layer where the collapse is taking place. Now, when a collapse is taking place, everything is falling apart. And if you want to model the wall falling in, caving in a very fast fashion, you need to take into account inertial effects. So we thought maybe dynamic is necessary. And because we were doing dynamics for part of the way, we felt that we can't do an effective stress analysis. Abaqus doesn't allow us to mix effective stress with dynamic analysis. So we can only do total stress. So anyway, that's what we did. And one of the things we did in those days, now in Plexis is very straightforward. You can upload the boreholes. But in those days, there was no such thing to upload boreholes. So as a result, what we did was that we took all the boreholes and we did we used the surface mapping software to layer out all the top and the bottom of each soil layer, and then we upload it onto the mesh using a program we developed ourselves. So it's quite a complicated thing, you know. And you can see there are many layers. This is actually the ground surface. Up to here, this is the followed, this at the bottom here is followed by this. So the whole thing stacked together, left to right. Okay? So this is what it looks like. And this is actually a sequence that we model. And you can see individual struts were modeled. Okay? Individual struts. Okay? Now, actually, the modeling of the struts, the modeling of the struts took a lot of effort because it's a curvilinear thing. It's a curve alignment. Because it's a curve alignment, your strut is never exactly X or Y or Z. It is some funny direction that is neither X nor Y nor Z. So, in a sense, this is the situation. So, basically, we model layer by layer, layer by layer, until the 10th layer. Then we start to go left. At the 10th layer, our excavation went from here down up to here, and then it sort of proceeded from the east to the west. This is the east direction. This is the west, so the excavation proceeds. We model the excavation in detail on the 10th excavation. Okay, up to the 10th, we felt that the computational time is too much. It took 2 months to run this job. Okay, it's too much. So we have to do it whole layer. But at the 10th layer, we want to simulate that collapse. And so basically, we do part excavation. Okay, so this is the situation. This is what we model. Okay, and okay. Oh, before I forget, did I have that? No. Okay, basically, before I forget, there are a few things that we actually put in, and that is that, you know, the diaphragm wall panels I mentioned to you yesterday. Every panel is cast with a concrete key, but there's no steel in between, so the panels can easily break up. Now, to allow the panel to break, what we did was we modeled every individual panel of the diaphragm wall separately without common nodes, but two separate nodes. And then between the two separate nodes, we put in linkage element. And this special linkage element will break when the strain exceeds 0.1%, which is the breaking, the fracture strain of the concrete. So basically, you can break up like that. So basically, that allows the wall panel to in a sense, break up. We want to model. We want to see whether there is a breakup action or not. So this is one of the things that we actually model. And then the struts, the bracings are modeled to allow buckling. We actually model buckling, and we model. Okay, so anyway, the struts are modeled to buckle. All right, and we actually model the P delta effect inside as well. The P delta effect. I don't know whether you are familiar with the P delta effect in the structure, in the sense that when the thing bends, then there is actually a moment between the caused by the two axial force. So the P delta effect was modeled into the whole thing. So the modeling was actually quite detailed. And we modeled the preloading. Individual struts, we modeled the preloading. Okay, so it's quite a tedious process. So anyway, this is the comparison between the measured inclinometer readings, and there are inclinometer readings just at the collapse section. the day before the collapse, measured day before the collapse, and our analysis. And you can see these are the sections, the strut sections, 333, 334, 335, 336, 337. They are sections. They are actually strut sections designation. If I'm not wrong, the strut sections are designated, I think, 333, 334, 335 in that order. So from the east to the west. So anyway, this is the situation. And so basically, if you look at it, this is the south wall. This is the south side of the excavation. The southern side, which is actually this wall. This wall. The other one is the north wall. And we were able to model both the deflection of the south wall and the north wall. And there's one particular thing that we were able to model which none of the expertness was able to model until they put in all kinds of... We didn't do anything. We just put in the soil profile as the borehole shows it. The funny thing was this. This is 400 millimeters. This was the one that was observed. Remember, 441 millimeter, 440 millimeter the day before the collapse. This is 200 millimeter the day before the collapse. Now you ask yourself, why is it that the south side is deflecting so much more than the north side? If you have a symmetrical excavation, then the two sides should be more or less the same, right? You expect the deflection to be more or less the same. So now, basically the southern side is deflecting almost twice the deflection of the north side. Okay? Now there is a very good reason for it. And now I'm going to see whether we can animate this thing. Okay, here we can see an aerial view of the south wall and the north wall deflecting in. This is an aerial view of the deflection. Okay, this is the section that collapsed. This is the circular shaft. Okay. Can you see the split here? This is no accident. We actually modeled that, allow it to split, and it actually splitted up. Okay, so you can see the split happening over here. So this is the original split, and then this is a secondary split because the curvature here is so large, it just broke the wall there. Okay, so this is the situation. Now we managed to push this analysis up to a maximum wall deflection of 5 meters. At that point, even Abacus just could not take it. I think 5 meter wall deflection is a bit, I mean, honestly speaking, I don't think softwares like GeoFEA, Plexis will be able to get near to that level of deflection. You know, so this is a huge deflection. And you can see the thing from third angle. This is the southern wall. This is the northern wall. And you can see we actually model the differences. The wall depth is not uniform, you know, and we model it individually. Okay. And you can see the maximum deflection is around where the 9-10 level strut is taking place. Okay. You can see that there's a bit of overlap, and that's because when we animate this, we actually magnify the deformed shape. So it looks but in fact the separation of the wall is a lot more than that. Okay, so basically you can see the whole thing. This has gone down. This has splitted up here. You can see this has splitted up here. Okay, and there are a lot of smaller splits along the way. So basically, the important thing is this: don't save on the whalers. You know what I mean? And there's a lot of unintended effect. The unintended effect is, yesterday I told you about the south wall. You can see the south wall is on the the convex side of the band. So when it comes in, the wall line is breaking up. It's actually pulling the wall line apart. And so as a result, you got tensile stress along that wall line, pulling it this way. And so therefore, there is the natural tendency to just break it up. You know? And that explains why the south wall is actually deflecting a lot more. Because my suspicion is that based on this run, the cracking already took place long before the collapse. Many of the joints are cracked microscopically, so you can't, it's just that they never pay attention to it. You don't know. Okay. So anyway, this was the collapse, and you can see the thing looking like tombstones, every one of them, you know, looking like tombstones. Okay, now there is no global whaler, and there's an example of having no. That's how they put it to the panel, which I think is absurd because the panels are not even face to face. Some panels are like that, some panels like that, and then this guy is in between two panels. How do you strut the two? To me, it's just unreal. Okay, so this is the This is the gist of the thing. Now, there are a lot of smaller details like the 66 kilovolt crossover. I won't mention to it, but I want you to take a closer look at this. This shows you how the strut buckle. You see the light cyan is the part that is slightly loaded. The dark blue are the part that's heavily loaded. You can see the thing jumping across from the east to the west. The light blue, I'm going to show you again. Just all light blue, and then the dark blue is happening. Then it jumped to the next one. It then jumped to the next view and jumped to the west. This is classic progressive collapse. As a few sections of the strut buckle, they lose the load carrying capacity. The wall comes in, it loads the neighboring section. The neighboring section gets overloaded. They buckle, and then it transmits the thing forward. You know. Okay, and if you look at the sequence of the buckled strut section, and here I have the buckled strut section. This is, this 333 is actually here. 333 is actually here. 334, 335. So 340 is the last one, closest to the east where the shaft is. So the initial section of strut buckle is a level 9 struts, this view. Then it propagated at some point later on to this view, and then it propagated to here. So it's propagating westward and upwards, the strut buckling. Okay, so this is roughly how the thing looks like. Essentially, okay, the main thing is that what this suggests is that the maximum movement of the south wall is larger than that of the north wall, and the inclined movement, and we think it is due to the fact that the south wall has a greater tendency to split up, to break up due to the tension in the wall line. You know, and the breakup might have led to the twisting of the strut that caused the buckling of the strut, causing the transfer of the load from bottom to the top. From bottom to the top. Okay? Okay, so there is possibly a contributory factor to the collapse, which is the absence of continuous or global veiler. So this is it. Okay? Now, the question is whether soil arching is an effective means of redistributing strut load. My personal sense is that we shouldn't rely too much on soil arching between panels of the diaphragm wall, because you really need a lot of differential movement, especially for soft soil. So this is not a good way of utilizing soil strength. I think it's a very risky way of doing it. So basically, what I hope to use this to show you without going through any more of the thing, essentially, is that let's see here. Without going through any more of this, it's just to show you that if you don't have to use a very sophisticated model. What you need to do is to have a very good consideration of how that process, what are the important factors that is featured in that process, and you model those factors inside, whether they are construction and whatever factors. There's nothing to say that constitutive factors are more important than any other factors. Is that all right? Okay. So any question on this? There are a few more slides, but I think we don't have to go through that. I mean, I tried to rub Andrew Whittle a little bit on his 2005. I think I don't want to say too much. I mean, we are friends, you know. We are not good friends. We are good, quote unquote, friends. Andrew Whittle is professor of soil mechanics, geotechnical engineering at MIT. He does come to Singapore a lot, and his main objective is to look for money. He thinks Singapore is the gold mine, so there's a lot of money there. But I think we are giving a lot of money to MIT, but not in geotechnical engineering. Yeah. We are giving a lot of money in terms of environmental and remote sensing, that kind of thing. I think we are doing quite a bit of that. But anyway, okay. So that is the first example. Okay. So I think we are doing quite nicely in terms of time. Are there any questions before we move to the second example? The second example. While we are on this set of slides. Yeah. There is a lot of you know, this kind of big collapse, and usually after a big collapse, there's a lot of after effect. So because of the collapse, let me go back to the first slide. What happened after the collapse? And this is not a technical thing, but it will be nice to show you what happened after the collapse. A lot of people lose money. That's the The gist of it is a lot of people lose money. Okay. And the guy who lost the most money is, of course, Nishimatsu, Nishimatsu is the one who lost a lot of money. Okay, basically, after the collapse, because there's so much debris along here, you really cannot push the tunnel through the same place again. There's a lot of steel beams and things that were never taken out, Yeah, not to mention 2 bodies inside. Okay, so basically what they did was they just covered up the whole thing, and then they re-divert the alignment of the tunnel so it goes here, which is about 100 meters further out towards the sea. 100 meters further out towards the sea. And that diversion and the rebuilding process, it cost Nishimatsu, the Japanese contractor, somebody was telling me the estimate was something like 350 million US dollars. 350 million US dollars. And they have to sell property in Japan to pay for that thing. And they were barred from construction project in Singapore for 3 years. So that was the main aftermath. And I think 5 of their the project director, a lot of project managers, few project managers went to jail. Not often Japanese in Singapore go to jail, but this happened. And one New Zealander, Paul Broom, also went to jail. Poor guy, that he's a real poor guy. You might say that it is a cowboy country in those days, Singapore, and as a result, can't be helped. He was in the whole thing. You see, like I told you, Nishimatsu is a contractor. All right, they want to design the temporary works that they have no one who truly understands geotechnical engineering design. They have a lot of people who are very good in driving schedules, project timing, but they don't have a guy so they brought Paul Broom. Now Paul Broom, at that time working for the Land Transport Authority, was not a technical person. He doesn't know anything about some geotechnical. In those days, you don't need to be a specialist professional geotechnical engineer to do this kind of job. And it was, in fact, after this that they come out with the new, that you need to be a geotechnical specialist for any excavation deeper than 6 meters. Alright? So basically, was brought in, and he was supposedly in charge of the finite element analysis, which is something he knows nothing about. The base file for Plexis was given by Monceau, like I told you yesterday, and it landed Monceau in trouble. Okay? And they just alter the base file. Just like what to you, the triaxial, this is the base file, you just change some parameter and run, Yeah. But it's okay, triaxial is okay, no problem. You can't kill people by modeling triaxial tests. Okay? But anyway, the base file was given, and so this was the situation. And Paul Broom was found guilty of professional negligence and sent to jail. So there were a total of 5 to 6 people who actually went to jail. Mostly Japanese. So essentially, that was the big thing. And then a lot of people who were sort of, in one way or other, affected by this development in the original days, so lose money. Including, I know there's one case because then they went to sue the Land Transport Authority, the expert witness for the Land Transport Authority, and I wrote the report I'm ashamed to say I whitewashed the Land Transport Authority. I think they are guilty, but I whitewashed them because they pay me money. Alright. Not exactly that, but I think that the situation is a bit more complicated. Either this guy is at fault or that guy. I think both sides are in a sense at fault. Okay, what happened was that there is another development somewhere out here, which is called Concourse, the Concourse building. Now, these Concourse people, I tell you these stories. These Concourse people thought, this train, there's a station somewhere here. This station is going to be so near to me that if I make a subway for pedestrians to walk through, they can easily come and do shopping at my place, and so I can earn a lot of money, you see. So basically, they part pay for that, and a lot of renovation work. And then suddenly, this thing collapsed, and the thing moved up 100 meters. Who is going to build a subway 100 meters to Concourse? It's never going to happen. Alright. So Concourse lost $16 million. Okay, so I tell you, there are all kind of unintended effects that can take place. And so they sued the Land Transport Authority for $16 million. And I think in the end, they got $1 million. Okay, so the amount of money that you're talking about is actually a lot. And my experience is that if you are game, and I can't take that kind of thing because the lawyers, they make you say all kind of things they want you to say. But if you are if you are okay with doing that kind of thing, in this kind of big project, wherever this kind of big project, you can earn a lot of money. Because if you are an expert witness, you typically, geotechnical expert witness will charge $600 to $800 per hour. Even you sit on the toilet bowl and you say, I'm thinking through the problem, you still charge $600 per hour. You take a shower, taking a shower, you're thinking about the problem. I'm thinking about your problem, so you jolly well pay me $600 per hour. You don't pay me, I'm going to walk off the job. That's exactly how it. So they will never question you over your timesheet, because you keep a timesheet. This time to this time, this time to this time. They will never question you because the amount of money that you charge, maybe 1 to 200,000 Singapore dollars, is nothing compared to $16 million or $300 million. I mean, what is it? It's loose change, to them. So they will just willingly pay you. Yeah. So basically, yeah, if you are game for that kind of life, But after about 4 jobs, I swear by all the holy books, I don't want to do it. Because honestly, first thing, the lawyers are very pushy. You say all kind of things because they think we're going to lose. Alright, and some of the things I'm really uncomfortable about saying it. The second thing is that you work day and night because when the report they need, where they don't care Saturday night, Sunday afternoon, National Day, your public holiday, jolly well work. Good money. So you can do it for a short time and then retire. Okay. So this is one of the situation. So does that sort of answer your question? Yeah. So basically there was a lot of, and one of the aftermath because of the nickel highway was, there were 14 parties, 14 lawyers, team of lawyers and expert witness representing the main contractor, all the subcontractors, then the aggrieved party, people who lost, the relative of those who lost their life in the thing, then the state, the government, the Ministry of Manpower, the Land Transport Authority, everybody is represented in there, and everybody's trying to say, it's not my fault, it's not my fault, it's not my fault. I mean, this is the way it worked. Okay? So basically, at the end of the day, what happened was that the inquiry was led by a senior judge. Of course, he knows next to nothing about engineering, let alone geotechnical engineering. Richard Magnus knows nothing about geotechnical engineering. In fact, he probably doesn't know that F equals to MA. Okay? So basically, he is helped by 2 guys, one structural engineer, and I don't even know why they appointed that guy. It's so hopeless. Anyway, the other guy is Tay Chi Ing from NTU. He's a soil guy, And basically, he sat through every day for about 1 year just to wrap up the whole thing. Okay? And so, essentially, out of what they found was that when this expert witness start talking about constitutive modeling, stress path, and method A, method B, and the guy who led evidence from the state, the lawyer, was a civil engineer turned lawyer. Civil engineer. These people make a lot of money because they understand a bit of this and that, so they can do litigation work. Now, that guy has a first degree from University of Auckland. But the guy also cannot understand what these guys are talking, because you just imagine a first degree guy it's like attending the first lecture in constitutive modeling without any introduction. How can he possibly understand what's going on? He wouldn't even know what is a stress path. So then they realized that there was this group of creatures running around called geotechnical engineer, who are doing all kinds of things underneath their feet and they know next to nothing about. And they thought, maybe we need to license this guy. Okay? So that was the thing that came out. Okay? And there was a big thing about why the structural engineer cannot do it. The structural engineer is fighting because they want to keep their turf. If you suddenly tell them you cannot do, if you are a structural engineer and I suddenly come and tell you any excavation deeper than 6 meters is out of your purview, straight away you lose a big chunk of business. You know what I mean? Straight away you lose a lot of business. So the structural engineer, no, we are good enough to do this. I sat in some of this meeting, it's just I mean, it's quite unreal, So basically, anyway, the ministers, the government made up its mind, so it came in. And now at the moment in Singapore, the aftermath in terms of geotechnical engineering, anything more than 6 meter deep excavation, slopes more than 10 meter high, foundations for building more than 30-story high, need to be done by geotechnical engineer. So these are the three main things. And as a geotechnical, to be qualified to be a geotechnical engineering specialist, you need to have a higher degree majoring in geotechnical engineering. So not just a first degree. First degree will not get you through. You need a higher degree majoring in geotechnical engineering. This is the one of the aftermath. Okay? Is that okay? Yeah. Any question? So this is some of the things that the stories that came out. But anyway, in fact, I did mention Nishimatsu did say that they did a job in the boulevard station and they never used Whaler. Yeah, but that boulevard station is a straight alignment. It's a straight line. This is a curved alignment. In a straight alignment, you can always make sure that panel to panel you get a you have panel to panel. Yeah, they face it. In a curve, one line is longer than the other line. You cannot ensure that. You cannot ensure that. That is the reason why they bring their experience from, you see, that's the danger. They brought in their experience from a job where the alignment is straight to a job where the alignment is curved. And the danger of that situation was not foreseen. But like I said yesterday, if you ask me to be a design engineer and I go in there, I walk in there cold. And I don't know, I have not thought deeply about this thing about the wall line buckling, pushing outward or pushing inwards, you know. I would have actually, I might have treated it as a plane strain design, to be honest. You see, that was exactly what they. So to me, it is very easy. So I mean, because someone asked, okay, why don't there are certain situations we can do 2D analysis? I say fine, but you have to foresee those situations. You have to judge those situations very, very carefully. You know, because all situations are inherently 3D. So the question you have to ask yourself is, if I do a 2D, what am I neglecting from that 3D? That is the question you need to ask. It's not like whether a 3D is necessary. You know, this problem is definitely 3D. What do I neglect? If I do a 2D, what am I assuming? What am I assuming? I think that is a far better question to ask than to say, do I need a 3D? You know what I mean? That is a more difficult question to answer, and it's a more dangerous question because it can easily lead you, oh, no, there's nothing 3D about it. You know, we just go and do a plane strain, and then that was exactly what they did, a plane strain. You know, but you can imagine if the wall line tries to break apart and you have whalers there, the whaler will help to hold it together. The whalers will have some effect in holding it. Yes, and but the whaler will definitely have a higher tensile capacity than the diaphragm wall because the diaphragm wall has no steel. Between them, they have no steel. It's just pure concrete. You know, just a concrete key. It's just a waterproof joint, really. So basically, whatever it is, you would imagine the whaler should be able to help you a fair bit. You know, whereas without the whaler, then you're totally fixed. But of course, the whaler will also help you to redistribute the load in a situation where your panels are not facing each other in a sense that, you know, this one is somewhere between two panels on the other side. So the whaler will help you to distribute the load in a more uniform fashion, you know, and keep the panels aligned. You know, I think the whaler will help, but you need pretty heavy whaler, in fact, in a situation like that. You know, the other thing is, of course, the walls are too thin. I mean, 35 meter. This is the first time I come across an 800 millimeter wall. Typically, we would go for something like 1.2 to 1.5 meter thick wall. So this is the situation. Let me just go to the Fort Canning Tunnel. Now, the Fort Canning Tunnel, I did the job in 2005. That is not a collapse event. Actually, I was very proud to say. Now it's open to traffic and there are lots of cars going through every day in, day out. So this is the Fort Canning Tunnel. So I will just use the other set of slides to show you a bit about, but you have already got this printout for the Fort Canning Tunnel. So I'll just quickly run through the Fort Canning Tunnel. Okay, the Fort Canning Tunnel is less dramatic because there was no accident. Alright, it actually was 2005, and they had a lot of problems. Okay, let me give you a background as to what is the thing with the Fort Canning Tunnel. There's an interesting story here, and this is Singapore politics at its best. At its best. 2005, 1 year after the Nickel Highway, nobody, for the whole year, the Land Transport Authority literally did not approve any job involving tunneling or deep excavation. All jobs were frozen for a whole year, because people were just too scared to move. All the engineers were too scared to move. So basically, nobody there to do anything. So basically, this Fort Canning Tunnel is a very special. It's only 180 meter, I think. 180 meter. It passed through a hill, a Canning Rise hill, very close to the center of town. Okay? And the tunnel is not very deep. The deepest portion was 9 meters below the road. The shallowest portion was 3 meters only below the road. And the tunnel is typically about 15 meter in diameter. I think it's 15 meter width. Actually a circular thing. It's a dome-shaped thing. 11 meter high, 15 meter deep, wide. So basically, it's kind of a dome shape. And the passes beneath the Fort Canning Rise. Consultant who was T.Y. Lin. I don't know whether you know T.Y. Lin International. T.Y. Lin International. They were actually a California company founded by this Professor T.Y. Lin, who is an expert in pre-stressed concrete, world authority, pre-stressed concrete. And so basically, they were the consultant for this job, and another Japanese contractor, not Nishimatsu, is Sato Koyo. Sato Koyo was the Japanese contractor, and they couldn't get this job approved. Okay, there was a lot of argument about this job, and I'll tell you more about the arguments later on. But essentially, they came to me to find, okay, can you do a 3D analysis? Very sophisticated, as sophisticated as you can do it. 3D analysis to simulate our process, our construction process, to prove to the Land Transport Authority that this is safe. My first question is this. Your thing is so shallow, why don't you just do an excavation? It is very good soil. It's bouldery clay. This is Fort Canning boulder bed. Bouldery clay, very stiff soil. There may be a few boulders around, but it's generally very good soil. Why don't you do an excavation? And you know what was the answer? There was one tree planted by Lee Kuan Yew that is not supposed to move. You know Lee Kuan Yew? The big name Lee Kuan Yew, our former Prime Minister, the founding Prime Minister of Singapore. When he planted a tree there, that tree is sacred. So you cannot die, you cannot move. Okay? And so the deep excavation was out of the question. Okay? So it has to be. So I said, what about a bored tunnel? He said, no, it's not worth it. It's only 180 meter. The contractor will never do a bored tunnel. Because you buy the machine already costs more than that. So basically, he said, the only way to do it is to use a new Austrian tunneling method, which is a sequential tunneling thing with shotcreting and all the rest of it. Okay, so this is the situation. And the argument between the Land Transport Authority was this. When you excavate the tunnel face, you push the face forward. There will always be a short length of unsupported, that means unshotcreted. A shotcrete portion. The shotcrete will always come after you push the face forward. The argument was, what was the length of that face you need to give? And the Land Transport Authority specifies no more than 1 meter. So every time your face moves forward 1 meter, more than 1 meter, you have to shotcrete. And that is cutting down the cycle very, very thin. And so basically, the contractor feels that it is wasting a lot of time. So the contractor is proposing 2 meter. 2 meter. That means you push the face, there can be a 2 meter gap between the face and the shotcreted portion. So this was actually the argument. Okay? So to settle this argument, we need to model the tunnel heading, which is obviously a 3-dimensional problem. More than that, we have to model the shotcreting sequence, the cycle of shotcreting. On top of that, the unsupported portion is not actually unsupported. There are actually 4 poles going forward. 4 poles, 12 meter long 4 poles going forward. Okay? And they are actually helping to support the so-called unshotcreted portion. So there are 4 poles, and we are supposed to model these 4 poles. Now, the consultant, the geotechnical consultant is an American tunneling guy called Kirk Seidler from New York, I think, from New York. In fact, we still correspond. Sometimes he still send me New Year cards and things like that. And he was doing 2D analysis. The problem with the 2D analysis is that you can never model the longitudinal beam action of the forepole. That is the problem. And you can only model a tunnel section. The forepole is as good as being useless. You know what I mean? So that's why you need a 3D analysis. So he come to me and said, okay, I'll do a 3D analysis for you. And it turned out to be a very complicated analysis. Very, very complicated analysis. So that, I'll just show you some of the things we did for the 3D analysis. So basically, there is a sequential tunneling. You can see that there's an upper bench. This is the upper bench. And there's a lower bench. So basically, you don't open up the entire tunnel cross-section at one go. In New Austrian tunneling method, you always do it left, right, top, bottom, that kind of thing. So that you open up bit by bit. You open up bit by bit. Okay, so this is the first thing we have to model the sequence of the tunneling meter by meter. Right? Then the second thing is we have to model the shotcreting. The shotcrete is modeled as 2 layers of shell to reflect the cross-anisotropy. Now, why is there a shell? This is one of those things when you're doing 3D analysis. You see, the guy who designed a lot of this geotechnical structure designed it on 2D. You see, a diaphragm wall panel, when you analyze diaphragm wall panel in 2D, it's just 2 wall panel like that. And there's no 3D action here. In fact, the joint between diaphragm wall panels are undefined, to say the least, undefined. Similarly for tunnel, you have segments of the shotcreting over here, and on the circumferential direction, the reinforcement is very well defined. They got steel bulkheads, they got all kind of things taking the thing. So you know exactly what is the stiffness, overall stiffness of the plate of the shotcrete. The problem is in the longitudinal direction. When we ask them, what stiffness? The guy said, I don't know, because most tunnels are designed to be stable in the circumferential direction. So all I did was I just put a few starter bars there. Okay, so what is the stiffness of the starter bars? Obviously, it's going to be much lower. So you have a plate element that is actually, in fact, cross-anisotropic. You know, cross-anisotropic. So as a result, we have to model that cross-anisotropy. So this is one of the things we actually model, okay, the cross-anisotropy. Now, later on, okay, this is the excavation sequence, and you can see starting like this, then the lower bench, and then you push forward, and so on and so forth. Okay, so basically the benching. Now, on top of the shotcrete, on top of the shotcreting, we also model the forepoling. And here you can see each forepole is one beam. So you can imagine how many beam elements go into it. And the forepoles are not there right at the beginning. They are there. Your tunnel is about, I think, they overlap, I think, 3 meters or 9 meters, can't remember. The forepoles overlap 3 meters. Okay? So every time you get near to the end of the forepole, there should be another set of forepole. They have to install new forepole. So the installation of the forepole is actually sequential as well with the tunneling. And we have to model that into place. So the forepoling has to be modeled. Alright? Then, the important thing is this. Because the shotcrete doesn't harden straight away. When you spray the shotcrete, it takes time to harden. And this is a typical hardening curve of a shotcrete. And depending on what you put into the shotcrete, it can harden very slowly or it can harden very quickly. So it depends. So these are some of the hardening that they actually found out from the test. So you got the strength, and then you got the time in terms of days. And you can see that the shotcrete, a lot of time, you don't reach full strength until about 28 days. Alright? Now, the rate of hardening is very important because cycle is 1 to 2 meters a day. And your gap is 1 to 2 meters. Your shotcrete has to build up sufficient strength before you can move forward. You get what I mean? So essentially what in fact is more important is not just the fact that you leave a section uncovered, but even the section that is supposedly covered but it has not reached full strength. And they are still deforming. So the question is, how does this affect the whole situation? So basically, anyway, this is just the forepole. We call it the forepoling sequence. The Japanese has a fantastic name for everything. They call it all-ground fastener or something like that. But it's actually just a series of pole with some grouting in between. Okay, but okay. Now, I want to take a look at this. This is a comparison. This one is our analysis. This was that came out about a year after. In fact, I chanced upon it because I was talking to one of the engineers and I said, hey, do you know that, he told me, he said, hey, do you know that there are few data for this ground settlement? I said, hey, why don't I take a look at it and see whether we can match up something. So we took a look at the ground data. This is the ground settlement. This is a measured settlement. And this is our predicted settlement. All right. The tunnel heading is actually about 20 meters ahead of this, which is somewhere around here. I think the tunnel heading is somewhere around here. Okay. It's about 20 meters ahead of the point of maximum settlement. So basically, you can see there's a settlement basin along the tunnel. The point of maximum settlement is typically about 20 meters behind the heading, not 2 meters behind the heading. So the important thing it tells us is actually your 1-2 meter is not going to affect the whole thing. The most important thing is how fast your shotcrete is hardening, because it affects the next 20 meters. It affects the next 20 days and therefore the next 20 meters. So basically what it tells you is this. In fact, if I'm digging the heading here, the maximum settlement is 20 meters behind me. It's 20, not 2 meters behind me. You know, and that is the thing. This is the nice thing about a 3D analysis. It can actually give you some insight that you never are aware of. And that is because the interaction between the hardening of the shotcrete, the digging and the unsupported length, the supported length and all that is very complicated. It's very complicated. So basically, it also tells you that you cannot dig too fast because then your shotcrete is not hardening enough when you go forward. You know. So basically, this is one of the things. And when we compare this thing with this thing, you can see this is perfectly symmetrical. This is the only thing. Finite element, you do this has to be perfectly symmetrical. So basically, when you look at this, this is about 130, slightly more than 130 millimeter maximum settlement. And if you look at this, this is about 110, 120, this is about 120 odd. So the difference is about 10 millimeter of settlement. 10 millimeter of settlement. 130, about 130 to 120, the difference is 10 millimeter. And the difference is about 10%. To me, for a first shot finite element, this is really a class A because we didn't have a field data. To me, this is pretty good. In fact, I think maybe we were on the lucky side. Okay, we did quite a few parametric study, and one of the things that governs, very important that governs it, is actually the permeability of the ground. Because the permeability of the ground happened to be quite low, 10 to the minus 7. So one of the engineers, when I presented to them, LTA, land transportation engineer, asked me, will there be a problem if the permeability goes up? Just as well we did the parametric study. That's why parametric study is very important. And what I was immediately able to tell him is this. If you ever hit a patch of sand with permeability 10 to minus 4, you are in trouble. Because your forepoling cannot hold back the sand. The sand will just go in between the forepoling. It will just fall right in through between the forepoling because it will drain out very fast. So basically the 10 to the minus 5, 10 to the minus 4 is the limiting permeability. You cannot afford a material with a higher permeability than that. Okay? And very luckily for them, they never hit any material with a higher permeability. But this is some of the things that a good FEM analysis will be able to help you foresee danger situation when you come onto it. You know. So this, I hope it will, let me see if there's any more thing. I'll show you some of the, okay, you can see the settlement trough. The settlement trough here, basically you look at it, this is really is about 20 odd meters from the heading. So basically to me, to argue over 1 meter or 2 meter to me is pointless. It's pointless. We are not even looking at the issue. The issue is that just because you spray shotcrete on it and there's some steel there, it doesn't mean the thing is fully supported because it's just cement paste, you know, when you first spray onto it. It takes 3, 4 days, maybe 7 days, 8 days to harden to the point where it can actually give you some support. You know what I mean? So in fact, you think about it, if I leave a gap of 1 meter, the effective gap may be 8 meters because you need about 7 to 8 days to do it, to harden. If I leave a gap of 2 meters, the effective gap is 9 meters. So what is the difference between 8 to 9 meter effective gap? Honestly, it's not 1 to 2 meters. 1 to 2 meters is 100% increase. 8 to 9 meters is less than 20% increase. So my point is, why argue over that when in fact the better thing to do is you better get a shotcrete that hardens as quick as possible, you know, and give you a high strength. That's what you need. Okay, so yeah. Okay, I can't remember now. I know that okay, the shotcrete on the side. I can't remember the number, but it is probably in the region of 150 millimeter to 200 millimeter all round circumferential. Now, there's also shotcrete on the facing. Every time you stop a cycle, an excavation cycle, you got to cover the facing. That I think is 50 millimeter or something like that. Okay, 50 to 100. And then the bottom here has to be covered with shotcrete. Has to be covered with shotcrete. Although you will obviously excavate the shotcrete, but it is also 50 to 100 millimeter. So I think it's about 50 to 100 millimeter along this temporary. This is temporary shotcrete because every time you push forward, for this phase when you push forward, you excavate the shotcrete. For this bottom here, when you push the lower bench forward, you also excavate the shotcrete. So it's a temporary shotcrete. In fact, all shotcretes are temporary because you will come in later on to do your permanent lining. But this side, the shotcrete over here is more permanent, and so they are about 150 to 200. And then there are steel bulkheads, not just steel bar, but steel frames, which are cast into the shotcrete. So, steel section, steel like I-beams, but yeah, they call it bulkheads, which are supposed to cast into the shot. So basically, you put in the thing first and then spray the shotcrete over it, so as to completely embed the section. The final lining we didn't analyze because the final lining took place much later, maybe 100 days later or something like that, you know. Oh yeah, no, the shotcrete is supposed to take all the displacement. The only thing is that the shotcrete does not have a lifetime of 100 years. You see, the shotcrete is temporary in the sense that if you have a permanent structure, your working life has to be about 100 years or more. The shotcrete doesn't have that working life. You see, so the shotcrete has a shorter working life. So sooner or later, you have to cover it with a permanent lining. You see, tunneling. The one thing about tunneling is this: I found out one thing. The moment you put in the permanent lining, nothing is going to happen because the design of the permanent lining is one of the safest thing in the world. You are designing for K0 condition. You know what I mean? K0 condition is one of the highest earth pressure around. So basically, once your permanent lining, most tunnel collapse when they are being dug. That is always the dangerous situation. You know, when you hit a patch of sand and boom, the whole thing come in like a swimming pool. You know, and then that's when you got problem. You know, or there's so much sand coming in that you didn't know then, and suddenly somewhere in front on the main road outside IIT Bombay, a big hole appeared. You know, yeah, it happened in Singapore. It happened. So basically, most tunneling incident happen. So when people tell me the permanent lining fail, when there was some research student in NUS who did cases, thankfully not my student, where they imagine the permanent lining fail. I said, since when this happened? Can you show me a real case where the permanent, because most engineers are very conversant with permanent lining design, even segmental lining. You know, the only time when you have permanent lining problem is what? When your tunnel settle. Now this is happening. I won't say it happens. It is happening in Singapore because some of the tunnels, even train tunnels, the small train tunnels, 6 meter to 8 meter diameter train tunnels, are dug in soil in reclaimed land that has been reclaimed 20 to 30 years ago, but are still settling. Singapore marine clay has a coefficient of consolidation of 0.5 meters squared per year. And that is very slow consolidating material. And so if you do a land reclamation and you do nothing to the soil, which is typically what happened, all right, it takes about 100 years to complete the consolidation process. So at the moment, a lot of soil is still consolidating, and some of the tunnels in recent years have been dug. Unfortunately, the new nickel highway also same thing has been dug in those, and they are settling quite a lot. So I don't know what happened. Honestly, I think this is a very sensitive issue. I know they are cracking up. Some of them are cracking up quite badly because the settlement is so bad. I mean, you just imagine if this thing starts to sag like that, the whole tunnel longitudinally, surely somewhere along the line there has to be some crack. You know, and some of the cracks are pretty severe. People who have walked in the tunnel told me they have come across locations within the tunnel where the water coming in is so bad, it's like you turn on a shower. You know? Of course, they have facility to try to pump the tunnel dry, but then as the water keep coming in and you keep wetting the tunnel, there will be a lot of what we call electrolytes in the solution, ions, basically ions in the solution. And this can lead to a lot of situations whereby there's a short circuit, and so there's a lot of stoppage. You know, every so often there will be some power outage and things like that. Because why? The third rail, which is the center rail, there's a power rail, somehow shorted out with some other thing and that kind of thing. It always happens. But other than that, if there's no major settlement, right, the permanent lining is pretty competent. Tunneling is always most dangerous when you're tunneling it. Yeah. Okay. Any question? Any other thing? Yeah. Sorry? Yeah, model the shotcrete as a shell. Okay, the reason why I have basically assumed one thing. We actually checked the stress in the shell. We have assumed that the shotcrete is behaving in a linear elastic fashion. Now, I do agree that if you overload the shotcrete, it can happen. But this shotcrete has a lot of steel inside. So my personal sense is that if you have a very densely gridded steel reinforcement, it will help to spread the load. And so the chances of local failure is actually less likely. So they actually had the design of the shotcrete is actually quite conservative. So as a result, when they asked me to analyze, they said that they actually designed it very conservative. So in addition, when we get the shell, the stresses from the shell, we actually give it back to their structural engineer, because the shotcrete is a structural design. It's a concrete structural design, so it's not a soil design. We give it back to the structural engineer to, in a sense, check the stress and make sure that it is below what, at the moment, actually, the bending moment and the shear forces are below whatever he has actually designed for. Now, the question is, why do we treat the shotcrete as an elastic material? I mean, that is the other question. The reason why I treat it as an elastic material is because I personally feel it is the most conservative way to treat the structural element. Because if you treat it as an elastic material, the stiffness of this thing will be high and it will attract the most load. Then when you pass that bending moment and the shear force to the structural engineer, you are giving him what you are getting, the highest possible bending moment. On the other hand, if you treat it as a non-linear material, that is a strain softening kind of material or plastic material, actually your bending moment will be limited by the plasticity of the thing. So when you pass that bending moment to the structural engineer, the bending moment will be lower. So I want to give the structural engineer the highest bending moment possible. And that's why I treat it as an elastic material. But the checking of whether the shotcrete is going to fail is based on the bending moment contour around the shotcrete. In fact, that was one of the things that the structural engineer wanted, the consultant, T.Y. Lin, wanted, because they want to check and make sure that the bending moment is not excessive. So that was the thing that we gave to them, the bending moment in the shotcrete. Okay. So I mean, this is really, I mean, at the end of the day, whether the shotcrete will actually fail locally or not, I guess it's a matter of judgment. I think it comes down to a matter of judgment. Yes. Yeah, but there are still bars in the shotcrete, whereas the panel has no steel bar in between. So the panels will crack right up. The shotcrete has a steel inside, and we don't use the overall section. In Singapore, the design of diaphragm wall and shotcreting they are very careful about it. You are not allowed to use the gross section. The EI. If you do a shell design, you got an EI that you got Young's modulus multiplied by the second moment of area, the EI. The EI that you use cannot be the gross section. It has to be the crack section. The crack section. So therefore, any section of concrete that is experiencing tensile strength is assumed to be cracked. And the only thing that's taking the tensile load is actually the tensile stress is actually the steel bars. So you need steel bars on the tensile side. So the shotcretes have all got steel bars on the tensile side. So the shotcrete, in that sense, is different from the panel. The diaphragm wall panel has no steel in between, because they are not meant to take load, transfer load across in this direction. But the shotcrete is meant to transfer load in the circumferential direction. That's why I said, in fact, designing for shotcrete in the circumferential direction, modeling it is actually quite straightforward. Modeling it in the longitudinal direction is more a matter of guesswork, because how many steel bars are used as a starter bars and things like that affect then your stiffness, your effective stiffness. Because they are using crack section. We are using crack section. We are not using cross section. So the crack section EI, the modulus, the section modulus, the crack section modulus in the longitudinal direction is much, much lower than that in the circumferential direction. Okay. So when you're designing in Singapore, there's one thing you got to note. They usually will insist that you use the crack section. You know, any concrete that is exposed to tension or on a tensile fiber is considered to be useless. Okay. Yeah. In fact, this is a consolidation. This is already a... Yeah. It's a full consolidation analysis. So that's why the permeability... You see, the reason why the 10 to the minus 5 is so critical as a boundary, as a limiting permeability is because if you have a material that has a permeability greater than 10 to the minus 5, then your uncovered section, which is 2 meters, is sufficient to allow the material to drain. Over that period, 2 days, is sufficient to allow local drainage. And then the material will fall through the forepoling, and then you'll get a failure around there. On the other hand, if you have a material that has a lower permeability, then this material will remain undrained for a longer period. And so it will hold the strength longer, and therefore you have a longer, in tunneling the word is stand-up time. You have a better stand-up time if the material is less drained. You know, when the worst thing in tunneling is to hit running sand, then you are really in trouble, because especially underwater table, the water will flush the sand in, and then there's nothing much you can do. You know? Yes, but it is a linear elastic model, but the stiffness is changing. We only model the stiffness. We didn't model the strength of the shotcrete, because as I mentioned, the shotcrete we want to treat it as an elastic material, to give it. But the stiffness was modeled using the formula, the standard formula for concrete or something like that. I think this is the one, 4.73 square root of FC MPa, and then the FC value is following the curve. So we actually work in a curve, you know. For what? Modify? Yes. Okay, that's a good question. I did not really address. The modified chem clay is meant for a class of clay called remolded soil. That is a soil that is supposed to have very little cementation. We are talking about real cohesion. There's very little cementation. That soil has very little cement. So it's a remolded soil. So that is the reason why the modified chem clay never bother about the cohesion, which is assumed to be zero. Okay? Now, on the other hand, if you have a soil that has a significant amount of cementation, the material that you will be treating it is like our cohesive chem clay. Like I talked to you yesterday about the cohesive chem clay, where we actually have you look at this, there's actually a cohesion work into the situation. So this is where the cohesion parameter, the capital C, is the cohesion parameter. This is actually where it comes in. So this is a soil that starts off with a significant amount of cohesion. The modified chem clay doesn't have significant. It only applies to remolded soil. Remolded soil means you remold it, and so there cannot be a cohesion. It's completely remolded. That is the logic. That is the rationale of the modified chem clay. That's why modified chem clay never considers cohesion. Now you might say that there is a class of material which is heavily over consolidated soil. Some people also measure cohesion, but the way the modified chem clay would address this issue is this. I need to write on the board again. Sorry to dirty your board. It says, what happens is And this you can find in a lot of textbooks. Lamb and Whitman actually says it. You read Lamb and Whitman Soil Mechanics, the book Soil Mechanics. They actually discuss the failure envelope for over-consolidated soil. And what they say is exactly what, and it is also shown in the BS 8002. Let me, you remember I showed you the pages from the BS, and if you look at the pages on the BS 8002, let me just quickly get back to it. You see this failure envelope over here. This failure envelope actually has a very interesting thing to it. This failure envelope is a straight line over here. This is a classic failure envelope that Imperial College people would have plotted for soil. And that is that for lightly over-consolidated and normally consolidated clay, the failure envelope is actually a straight line. And the reason is because when you have a soil that is slightly over-consolidated or normally consolidated, there's no peak strength. It just goes into the critical state. So what you are measuring then is the critical state line. This is part of the critical state line. Okay? And on the other hand, if your soil is heavily over-consolidated, then you have a peak strength. So the peak strength envelope is actually reflected here. This is the peak strength envelope. Now, if you look carefully at the peak strength envelope, in fact, it is a curve. It is not a straight line. It is a curve. And this was also highlighted by Lamb and Whitman, who says that, in fact, the peak strength failure envelope is actually a curve for over-consolidated soil. So what they say is this, that if you plot the failure envelope of a soil, all right, in fact, of a heavily over-consolidated soil, in fact, it looks something like this. All right, you take 3 more circles, they are never perfectly aligned. One of them will be, it's usually like that. All right, so the question then is how you want to plot. You want to follow the first and second circle and deviate a little bit from the third circle, or you want to follow the second and the third circle and deviate a little bit from the first circle, or you want to follow the first and the third circle and cut through the second circle. It's a matter of judgment. All right, that's why there are people who, for the same 3 more circle, if I give it to you and I give it to him, you probably end up with a different set of C dash and Phi dash. Because he may take the first and the third circle and you may take the first. You're not wrong, he's not wrong. You know what I mean? But the important thing is that the idea of the Mohr circle, say this is, when you draw the, when you look at the failure envelope, it's actually like that. But they always tell you, engineers don't like a curve. They like a straight line. So I easily just project it back. So this is the reason why they actually idealize it to a straight line. And when you idealize it to a straight line, very often it doesn't pass through the origin because it's a curve. Alright? So as a result, you end up with what they call an apparent cohesion. The apparent cohesion is something that comes out because of the way you fit the curve with a straight line. You draw a straight line through the curve. Now, I have seen residual soil, not heavily over-consolidated, but residual soil is more common in Singapore. I've seen people giving very high cohesion and very low angle of friction. And I've seen people giving very high angle of friction and very low cohesion. Very low cohesion. And the reason is very simple. If you draw a straight line to curve down here, your angle of friction is very low, but your cohesion is very high. Okay? On the other hand, if you fit the curve around here, then your angle of friction is very high, your cohesion is low. You know? So what I'm trying to show you is that the cohesion you get there, in the view of the chem clay and critical state soil mechanics, for this class of soil, over-consolidated soil, it is not a real thing. It is the way you fit a curve. And in fact, if you read the BS 8002, the BS 8002 recommend this way of treating it. Don't use cohesion. Don't use cohesion. What they say is this. You think of, this is the curve, right? Typically, you would use something like that, or then you get a cohesion coming down. Then you get a cohesion intercept, a non-zero intercept. Agree? Now, what they say is this. Don't do this. You do this. You take a point where you think encompasses your stress range of your interest, of your design. And you just pass the line here from the origin to this point. That is a C angle of friction. Gives you a higher value than your critical state value. Now, there are some people who will give you value of peak angle of friction that's lower than the critical state value. Possible. It is possible because of the way you fit a curve. This is the critical state angle of friction. If I fit a curve like that, my gradient will be less, for sure. So therefore, I end up with a lower angle of friction than the critical state angle, but I have a certain cohesion. All right. The PS 8002 said, I recommend you don't do any of this thing. Just do this. Take the 0 point and go right up to where you are. You always end up with a higher angle of friction than the critical state. That is the design philosophy of PS 8002. Is that okay? So basically what I'm trying to say in a nutshell is that the cohesion that you get from a heavily over-consolidated soil in the view of the critical state soil mechanics concept is a fictitious quantity. It's the way you fit a curve. In reality, it is a curve. And the reason why it is a curve is because this is, remember what we discussed yesterday and the last week? This is the point where this actually doesn't represent the failure envelope. This represents the U locus of the soil. And the U locus of the soil, as in the chem clay model, is a curve. It's not a straight line. Is that alright? Okay, so basically you're just fitting a straight line to a curve. You're just forcing a curve to a straight line. So basically, for example, in Singapore soil formation like Bukit Timah granite, they have a whole range of C dash value from 0 to 50. And then the angle of friction ranges from 24 degree or 22 degree to something like 35 degree. It's a question of how you want to make your cup of tea. You know, how you want to fit your curve. 1 sugar, 2 sugar, no sugar. You know what I mean? So that's the way when I look at all those numbers, you know, it occurred to me that basically my guess is as good as their guess. You either have a very high value of cohesion, okay, and a low angle of friction, or a low value of cohesion, maybe near 0, and a high angle of friction. Okay. This is the view of critical state soil mechanics. That's why for critical state soil mechanics, they don't actually use the cohesion intercept. But when I deal with cement treated soil, I actually do acknowledge that there are some material. Now, the way they will tell you how to assess whether that material has real cohesion, true cohesion. What Andrew Schofield called true cohesion. Very simple. You take a lump of soil, you put it in water, you come back 2 weeks later, is it still a lump of soil or has it become a powder floating in a solution? Many over-consolidated soil like old alluvium in Singapore, when you put it into water, after 7 days you come back, you see nothing. Just a suspension. Just a suspension. There's no real cohesion because you put it in there, zero effective stress. After a while, it will just dissipate. On the other hand, you put a lump of concrete in the water, you wait 10 years, it will still be a lump of concrete. That's real cohesion. Is that alright? Okay. So this is the way we justify. In fact, when we wrote some of the papers, we justify that it has real cohesion because you see, after 7 days, the thing is still standing there nicely. There's nothing wrong with it. I mean, there's zero effective stress, and yet the guy is holding his shape. Something must be there. Alright? If it is just apparent cohesion like this, you put it under zero effective stress completion, there will be no strength. It will just disperse. The moment the negative pore pressure dissipates, end of the story. Okay? So the best thing you can do is to just immerse it in the water, wait for 7 days or 2 weeks, come back, take a look, see what happens. Alright? Anything else? Okay, if not, then I actually don't need the second session.